welcome back, chemistry students. It's Dr. Tullis here. Hopefully you feel comfortable writing equations for acid-base reactions and deciding whether they're product or reactant favored at equilibrium. Now you're going to be able to predict whether the solutions resulting from acid-base reactions are acidic, neutral, or basic. The reaction of hydrochloric acid and sodium hydroxide is a classic example of a strong acid, strong base reaction, where the reaction of citric acid and bicarbonate ion represents the reaction of a weak acid and a weak base. These are two of four general types of acid-base reactions. Because acid-base reactions are among the most important classes of chemical reactions, it's useful for you to know the outcome of the various types of these reactions. Like I said, the first reaction type, we have a strong acid and a strong base. Now, hydrochloric acid we know is a strong acid. We know acids are proton donors. So this H is going to separate 100% from Cl. So we'll have H plus and Cl minus, Na plus and OH minus. That H and that OH are going to join to form water, and the Na and the Cl to form sodium chloride. My net ionic equation is going to be H plus OH minus to give me liquid water. Mixing equal quantities of a strong acid and a strong base produces a neutral solution, hence the water there. The second type is if I have a weak acid, like hydrocyanic acid or formic acid, and a strong base. How do we know if it's a weak acid? Well, it's not a strong acid, and it has a Ka value associated with it in our chart. Strong base, we know, is a hydroxide. So if I have a weak acid and a strong base, and I mix equal amounts of a strong base and that weak acid, it will produce a salt whose anion is the conjugate base of the weak acid. So for example, HCN will produce Cn minus. Formic acid will produce formate. The cation, for example, in the sodium hydroxide, the sodium is a group 1 cation, so it gives a neutral solution. The solution is basic, with the pH depending on the Kb for that anion. So here's our weak acid and our strong base. Again, our Na is just kind of floating around up here. So there's our OH, and there's our strong base, our OH. We know that the acid is a proton donor, so the H will join with the OH. Each one of these has water as a product. And then we have both of those anions of the acid over here. So we know that the OH is a much stronger base than either of the other bases. So the reaction will go to the right. We know strong pushes away from it towards the weak. Now what if I have a strong acid and a weak base? For example, hydrochloric acid we know is a strong acid, and ammonia is a weak base. If I mixed equal amounts, it would produce a conjugate acid. For example, HCl, we know that acid is going to donate that proton, so NH3 becomes NH4. And then we have our chloride ion here. So we have the anion, which in this case has no effect on the solution pH. So if this has no effect on the pH, we're left with NH4, which is going to make it acidic. And that pH depends on the Ka for that acid. Again, we know that HCl over on the left is much stronger than the conjugate acid on the right, so the reaction will proceed to the right. Additionally, if I compared the Kb value of NH3 and Cl, NH3 wins out. So our strong acid, stronger base are on the left, so our reaction goes to the right to reach completion. And the fourth one is if I have a weak acid and a weak base. The reaction is going to be product favored because acetic acid is a stronger acid than NH4, and NH3 is a stronger base than acetate, and we would look at the Ka and the Kb values. So if I mixed equal amounts of the weak acid and the weak base, we produce a salt whose cation is the conjugate acid of the weak base, and whose anion is the conjugate base of the weak acid. This just labels that conjugate base of the weak acid. That would be my acetate, because my acetic acid is the weak acid, so this is the conjugate base. And the conjugate acid is from the weak base, and the pH will depend on the Ka and the Kb values. If you want to pause, this just kind of breaks it down. We have a strong acid, strong base, strong acid, weak base, weak acid, strong base, weak acid, weak base. Pause the video here to see if you can predict if the resulting solution will be acidic, basic, or neutral. It would be neutral because I have a strong acid and a strong base. Pause here. This would be basic because I have a strong base and a weak acid. So if I set up my reaction here, we have HF, my weak acid, my strong base, again dissociated into our K plus ions, which has no effect on the solution, and my OH minus. My H and OH will combine to form water, and I'm left with the conjugate base of that weak acid, and that fluoride is going to make it basic. Pause here and try this one. Again, I'm going to have a neutral solution because I have a strong acid and a strong base. Pause and try this one. Here I have a weak acid and a weak base. So if I look at my products, my conjugate acid of the weak base is going to be NH4+, and the conjugate base of the weak acid is F-. So we can't determine if it's going to be basic, neutral, or acidic. We would need to look at the Ka and the Kb values to determine which one is bigger. Pause the video here. Here I've got a strong acid and a weak base. So we're going to have an acidic solution. That NH4 is definitely going to be much stronger than that chlorine. In this next section, we are going to be able to calculate the equilibrium constant for a weak acid or a weak base from experimental information like having the pH, the hydronium or the hydroxide ion concentration. We can use the equilibrium constant and other information to calculate the pH of a solution of a weak acid or weak base. And we'll be able to calculate the pH after an acid-base reaction. Here we have an example where we need to determine K from initial concentrations and pH. We have nitrous acid, which is a weak acid, and water. So we can see that we know our acid is going to be a proton donor, giving us H3O+ and leaving us with NO2-. We then can make our ice table. We have HNO2, that's our reactant. We don't include water. And we have our two products, the concentration of H3O and NO2-. In order to get K, we need to know the equilibrium concentrations of each of these species. So let's get there. We were told that we started with 0.1 molar of HNO2. That's our initial. And we know that initially we have no product formed. We know that stoichiometrically we lose reactant and we gain product. And therefore at equilibrium, here are our concentrations. So let's set up our Ka expression. Our product would be the concentration of H3O+ times the concentration of NO2 all over the concentration of HNO2. All right, so at equilibrium we have X times X divided by 0.1 minus X, which then can simplify. X times X is X squared over 0.1 minus X. Now let's think about what X is. If I look back here, X is my H3O+, the concentration of my hydronium ion. Well, I was told that I knew the pH was 2.17. So I can take this one step further and I can say, well, 10 raised to the negative pH will give me my hydronium ion concentration. So 10 raised to the negative 2.17 is 6.76 times 10 to the negative 3. That is X. So let's plug that in to my X values to get Ka. That would give me 4.9 times 10 to the negative 4. Let's go the other way around. Let's determine the pH from initial concentrations and K. If I have H2S, a weak acid, in water, my acid will donate, so my one product will be H3O+. My other product will leave me with one less hydrogen, so HS minus. I'm given my initial concentration of my weak acid, and I'm given Ka. So let's go through and do our ice table. I started with 1 molar of my weak acid. Again, I have no product form. I will lose reactant and gain product, leaving me with my equilibrium. I set up our equation here, our Ka, which is equal to our products over reactant. X times X is X squared over 1 minus X. And that's equal to the Ka value that we were given. Let's solve for X. Once I set this up and I cross multiply, I would say that x squared is equal to 1.0 times 10 to the negative 7 times 1 minus x. And I could distribute this and say that x squared is equal to 1 times 10 to the negative 7 times negative 1 times 10 to the negative 7x. And we could get the quadratic formula here if I subtract x squared from both sides. If we look at our initial concentration, and in this case our initial concentration was 1 molar, and if that is greater than or equal to 100 times Ka. So our Ka is 1 times 10 to the negative 7. So 1 times 10 to the negative 7 times 100 is equal to 1 times 10 to the negative 5. This is still a really small number. 1 is definitely greater than this number. If that's the case, we don't need to go this far to use the quadratic equation. We can say that that difference, 1 minus this super duper small number, is pretty much going to be equal to that initial value. So we can get rid of that minus x. That can make this go a lot easier. And we can say then, take this equation but get rid of that minus x. X squared over 1 is equal to 1 times 10 to the negative 7. Then we can multiply like this and say, well, 1 times 10 to the negative 7 would be 1 times 10 to the negative 7 is equal to x squared. Square root both sides, and we get x is equal to 3.2 times 10 to the negative 4, and x is equal to H3O plus's concentration. So the negative log of our concentration of hydronium ion would give us a pH of 3.5. So continuing off what we just said, for weak acids and bases, we can approximate ionizations. That way we can avoid using the quadratic equation, but we have to check the validity of the assumption. Simplifying assumptions that produce an X value of less than 5% of the initial concentration of a reactant are acceptable because they produce negligible errors in the value of X. Again, we can do this whenever the concentration of the original concentration of the weak acid is greater than or equal to 100 times the value of Ka. Let's do an example here. We have 0.1 molar aqueous lactic acid and it has a pH of 2.43. What is the value of Ka for lactic acid? So it's a weak acid. Here's what we've got. We've got our lactic acid here. I just copied down what the equation gave us. And we know that's a weak acid. So we've got our weak acid in water. We know that we're going to donate that H, leaving me on the right with H3O plus. And we're going to have our lactate ion, which is the same thing minus an H, so it has a -1 charge. I wrote my Ka expression, which is just my products over the reactants. Let's set up our ice table. We were told that I initially had 0.1 molar of my lactic acid. And initially I have no product form. We know we're going to lose reactant and we're going to gain product, leaving me with 0.1 minus x over here, x and x. I was told on the page before that the pH was 2.43. Well, if I know the pH, I can find the hydronium ion concentration by doing 10 raised to the negative pH. And if I know that, I can plug the value into my hydronium ion concentration here at equilibrium. That gave me 0.003715. So that's my value of x. And then I can plug that in to this. When I plug 0.003715 into my lactic acid equilibrium, 1 minus that, I get 0.0963 molar. We can see that it's such a weak acid that very, very little of it ionizes. And the equilibrium concentration of lactic acid is essentially equal to the initial acid concentration. We're approximately 4% less. If I were to look at the difference between 0.0963 and 0.1, it's less than 4%. So this is one of those examples where the equilibrium concentration of the acid is essentially the initial concentration. So if I were to set this Ka expression up and I said x times x over 0.1 minus x, I can say, you know what, that difference is so little, we can just neglect it. So let's plug in our 0.003715 and square that and put that over 0.1. Then we can solve for Ka. And we would get a value of 1.4 times 10 to the negative 4 for my Ka value for this weak acid. Let's look at another similar example. We have a solution and we have 0.055 moles of butanoic acid in 1 liter. So therefore I have, this is my concentration because this many moles divided by 1 liter gives me 0.055 molarity of my butanoic acid. The pH is 2.72. So let's go right off the bat and do 10 raised to the negative pH to get the H3O plus concentration. There we go. I got 1.91 times 10 to the negative 3. Let's set up our ice table. This is my I, and I know that I initially have no products. We're going to lose reactants and gain products, leaving me with 0.055 minus x, x, and x. Let's set up our K expression. Notice that I didn't drop off the minus x in the denominator because if I took 1.91 times 10 to the negative 3 and times it by 100, I got 0.191. And 0.055 is not greater than 0.191 or equal to. So I'm not able to drop that x in this case. We have to put it in there. Plugging in my hydronium ion concentration into x, into my Ka expression, I got a Ka value of 6.8 times 10 to the negative 5. See if you get the same thing. See if you can set this one up. Calculate the concentration of H3O plus and the pH of a 0.02 molar solution of benzoic acid, and we know the Ka. Did you set up an ice table? Now let's set up our Ka expression. Ka is equal to x times x divided by 0.02 minus x. I simplified x times x to x squared and plugged in my Ka value. I then took 100 times my Ka value, and that would be 6.3 times 10 to the negative 3, and that's nowhere near that initial concentration, so I'm going to pretend that that does not exist, leaving me with x squared over 0.02. So let's multiply these two together and then take the square root of it because x squared is going to be equal to 0.02 times 6.3 times 10 to the negative 5th. So if I square root both sides, that will leave me with x. And I got 0.00112 molar. And that x is my H3O plus concentration. Now we need to take that and let's find the pH. To find the pH, it's the negative log of that hydronium ion concentration. So the negative log of 0.00112 would give me a pH of 2.95. And because I started with 2 significant figures for my concentration, I should end with 2 significant figures for this concentration. So 0.0011, that 2 would be left off. Here's another one. Pause the video here to see if you can solve it. Let's see how you did. I set up my ice table. I have my acetic acid and water to give me the acetate ion and the H3O plus. I initially started with 0.1 molar and none of my products. I lost x, I gained x, leaving me with x, x, and 0.1 minus x. So I set up the Ka expression. Ka is equal to x squared because x times x is x squared over my reactants, which is 0.1 minus x. I then simplified it, put in my Ka value that I was given here, and I said, you know what is 100 times that Ka? And that would be 1.8 times 10 to the negative 3. That is a lot smaller than this 0.1. So to make my math simple, I got rid of the minus x. I multiplied diagonally, and then I took the square root to get x was equal to 1.3 times 10 to the negative 3. Well, X is the concentration of H3O plus and the acetate ion. And then to get my acetic acid equilibrium, I did 0.1 minus that 1.3 times 10 to the negative 3. And I got a concentration of 0.099. We can see how little of it ionized, the difference between 0.099 and 0.1. So to get the pH, I took the negative log of my hydronium ion concentration. I got a pH of 2.87. Here's the ice table setting up our Ka expression. But we might have ran into a little hiccup here, because if I took 100 and times it by my Ka, I would get 0.018. Now my initial concentration of 0.001 is not greater than the 100 times my Ka, so I can't drop that minus X. So we're going to need to do this completely. So I multiplied and then I distributed, so that gave me my 1.8 times 10 to the negative 7 minus 1.8 times 10 to the negative 4x is equal to x squared. I subtracted x squared from both sides, so I have to use my quadratic equation. My A would be negative 1, my B would be negative 1.8 times 10 to the negative 4, and my C value is 1.8 times 10 to the negative 7. Plug that into your calculator to solve for x. When I plug it into my calculator, I get a positive value and a negative value, and obviously the negative value doesn't make any sense. So I got 3.44 times 10 to the negative 4th, and that x value is my hydronium ion concentration as well as my HCO2 concentration. And then to figure out my acetic acid concentration, I'm going to do 0.001 minus my x to get 6.56 times 10 to the negative 4th. And to get my pH, I'm going to do the negative log of my x value. And that would give me a pH of 3.46. And that wraps up this section.